embedded software testing, Unit 2. This will be the last session of Unit 2, and we study about some of the white box testing techniques and understanding of testing aspects. In the previous session, we studied about gray box testing, which is nothing but a, a mix of white box as well as black box test, where tester has a knowledge about internal details of the system as well as the system knowledge. With the help of that, and he will do the testing. This is actually very effective when it is coupled with error guessing, where with the help of the system knowledge, he will guess what sort of errors could come. This is particularly useful when we have a stable system working with a legacy code and there are certain changes or new functionality has been added to the embedded system. Also, we studied about test driver and test hub. It's a very important part of the embedded software testing. Test driver is software which executes software in order to test it, providing a framework for setting input parameters, executing the unit, and reading the output parameters. So basically, test driver will invoke the test which we want to test it. That is also a software piece with whatever the values that we want to provide as inputs and expect the outputs. Test hub is a replacement of the existing unit. So this is used in place of the real unit to facilitate the testing. So this is the framework that is being used for test hub and test driver. This is called a test bench or test bed, basically. So the unit is getting used by the driver, test driver, and unit can be replaced with the help of a test hub. So test hub and drivers are part of the test bed, and the unit will be subjected to test. Okay, coming to the various aspects of the tools that are used in white box testing. Basically, they use for coverage purposes, and we have studied about commercial tools such as VectorCast for covering, for getting the reports of the coverage, and we also went through on LDRA, it is from LDRA.com, and IBM RTRT, so which has a facility for doing the test steps, building the executables on the target, and generating the reports. Also, we studied about logic analyzer, which will help in recording the memory activity in a real time or runtime, and records uh, the changes and the updates that are happening in the embedded software. It basically captures the events that are happening, and it is called a trace. It is particularly useful for interrupt-based applications where more interrupts are there, and the frequency of the interrupts are more. Also, we had a study about software performance analyzers. The performance could be from memory, timing, and load, speed, etc. So performance testing and tuning is very important aspect because that will drive the functionality, and especially if the software has to be upgradable or maintainable, so the performance has to be absolutely right. Then only we can do the rest of the testing. So this is a very important aspect, but sometimes in the industry this will be taken as a last priority. But as per me, this should be a topmost priority for doing the embedded software testing. Also, there are various types of memory testing we do. So especially they look for the memory usage, how the memory is being used in the embedded software system. And there is a map file, and the map file will be detailed in terms of how much stack, how much constants are using, what is the size of the RAM, what is the size of the flash, etc. And for testing each of these memory parts within the embedded software, basically the software itself will have facility, and it will be keep on checking in every fixed intervals or cycles of the system life, and the reports will be generated or hooked with the external tool to get the data, and that will be analyzed. So basically, the RAM, the memory, flash will be checked with the help of integrity tests. Integrity tests could be working ones or a pattern tests. NVM also uh, will be tested with the help of pattern test or working one test, where the ESCO prompts are used for fault recording and storage. And the timing analysis we can do with the help of integrated development environment. With the help of debuggers, we can analyze the interrupt service routine and the various events that are happening with respect to time. And as a black box, so if you want to test it, we may have to use ports if it is available within the embedded system. And those ports can be scoped using the oscilloscope, and oscilloscope will be analyzed with respect to the plotted graph of timing with respect to various events. Also, the embedded system has registers with respect to time, such as RTC, watchdog, etc. Those will be used as well in terms of analyzing time. Also, we went through the testing tools life cycle, how the life cycle has the life cycle can be used with respect to the tools. So we have a planning and control of the entire testing life cycle, which has preparation, specification, execution, and completion. For preparation, we have tools such as case tool analyzer, complexity analyzer. For specification, we have test case generation or test case generator, such as Perl or Python scripts or Excel sheet programming from the requirements. And also we have execution in terms of test data generator, simulators, debuggers, whatever we have studied so far. One of them or many of them could be used for execution purpose. And we have the completion and reporting mechanism of the executed parts. For planning and control, we use defect management and test management and traceability, etc., with respect to the requirements to the testing. Defect management we have studied uh, depending on the size of the project, the type of defect complexity and all that will be managed. There's a database and all that they'll be used in order to get the report of the defects as well as the requirements traceability. And in terms of scheduling and all that, they use different types of tools such as MPP and TestLink, Bugzilla, whatever it is, can be used in addition to the scheduling. This will help test management and progression of the embedded software testing. Test case preparation specification are done with the help of case tool analyzer, complexity analyzer, test case generators. For specification, they use it. Execution, we have seen stubs and drivers, simulators, emulators, debuggers, static code analyzers, performance analyzer, timing analyzers, code coverage analyzers are used. These are all basically used in white box testing as well as black box testing. Okay. Okay. In today's session, we will study more about the white box method, how they are getting implemented and how they can be executed, and in what way we can automate it. So basically, test automation is a process or a test method or whatever testing aspects that can be applied for testing the embedded software. So basically, test automation is used to minimize the time needed for test execution. So why we need test automation is, so we'll keep on doing the embedded software testing again and again, and similar requirements, similar sort of test cases. So we need to have a common framework, and the common framework will drive the entire system to test, and we'll feed the values with respect to each test cases, and that is why the test framework along with execution, the test automation is useful. So Automation is very profitable in terms of time, money, and quality, but it needs an initial investment of time, one time. Once it is done, the framework is available. It's very uh, easier to maintain as well as run the tests automatically. So very less human intervention is required in terms of testing, and also it can be used to repeat reoccurrences of test procedures. That means multiple tests of similar procedures. We don't need to do it manually. We can do a batch processing, batch automation. It's also called as. So test automation will help in doing these things where multiple procedures are to be executed in a batch. And some tests such as statistical usage also can be done with the help of test automation. Testing and evolutionary algorithms are impossible without test automation. That means there are certain things which are of a repetitive nature or algorithms which keep changing. We have a set of data and there are fixes and we may have to do regression. So we cannot afford to have a manual effort again and again spent on that. So in that way, it is very useful to have test automation. So basically, in principle, the execution of almost every test can be automated, uh, depending on type of test. In practice, so only a small part of the tests are automated, uh, in depending on the project again. But the automation will be done most of the requirements where similar functionality or a group of functionality can be tested with various inputs or where multiple test cases are being executed. So basically, test automation is often used in different situations where tests that have to be repeated many times. A basic test with a huge range of inputs are there. The same steps have to be executed every time, but with different data. Uh, Very complicated or error-prone tests. That means we have a piece of software having more errors and all that, and every time different errors are coming. So it is better to automate it so that minimal human intervention is used for that. So this is very useful for complicated tests. But testing requires specialized equipment which will generate the appropriate input signals, activate the system, and capture the output and analyze the output. Analysis can be done manually or the tool itself can be used in terms of analyzing it. Okay, so continuation of our test automation. So we can have the control of our test automation with respect to changes in the system. Design and requirements are common and are also threat to the usability of the automated test. So, so what will happen is we have test automation completely for the entire bunch of the embedded software and the requirements. Sometimes the changes or the fixes that could happen to the system or the tests that are going to be applied for the system. So the consequences of those changes could be changes on test cases, additional test cases are added with the different aspects. When different result checks are there, and the framework has some impact in terms of modifying it. System interface has changed. There's a change in functionality. So signals have changed. Target platform is different. From one build to another build, there are different hardware boards. Different version is being used. Then there is a possibility that automation may fail or collapse. So control of the test automation is very important. We should have scalability of the test automation also. Automation equipment or tools or scripts that are developed should be more generic than specific so that it is very maintainable, and all the specified consequences of changes will have a less impact on modifying the test automation. Updates and regressions. So basically, automated testing saves money and time, and quality will be better because less human intervention is there. We are depending on the system and the tools or the framework, and the framework is stable. Once you make it, it is expected to behave the same way. So chance of injecting error by the user is very less, and several times that test can be reproducible. So this is also very important, reproducibility of the test execution, pass, fails, etc. is easier with the help of test automation. So this means that the automated test should be used for consecutive releases or in different stages of development. That means the same sort of a automation should be able to use for different releases of the software build and the equipments. The embedded target could be. So which also means that automated tests have to be designed to deal with these uncertainties due to change in the system design requirements for all this. So we will see how automation tests can be implemented technically in a nutshell. Basically, we'll try to understand that. And automation test basically being developed in-house with the help of commercial tools, basically that are available in the market. And of course, those tools have to be foolproof and should be qualified, especially in the industries of automotive and aerospace. So very important because it has to be reliable and we need to produce the consistent results all the time. So then also we'll study about how the process of introducing automated testing and similar development process such as requirement design, deployment and maintenance. Okay, so test automation techniques, automated testing, executing tests using an automated test suite. So there is a test suite that will be used, which will be executed for testing the specific software piece. Test suite, everything necessary to execute a test by pushing just one button. Ideally, there should be that actually. Test suite will be triggered and it will take care of all controlling, picking the data, signals, and driving values and getting the result, analyzing it, reporting as pass or fail is all part of the test suite. Then the test automation should be data driven, an approach where physical test actions are separated from test data, and the test data is the impulse for the test. Okay, this should be data driven, and there should be a framework in the end where a library of reusable models and design. That means as you see the test stubs and drivers, they should be reusable for many parts of the system. So test steps, test drivers, then common templates, or it is it could be a minimum sequences in especially I have seen LabVIEW and Simulink. It's very important. The sequences, the minimum templates, they develop it and they can use it as a plug and play for wherever they want to use within the complete automated testing system. So there is a test suite. Test suite will use this framework for the need of that particular test. So to maximize maintainability, flexibility, and ease of use, so some decisions, design decisions have to be made. uh, to avoid a test suite from becoming self-where it is designed to be as independent as possible of changes so that the framework can be used. So it's very important to have a test suite and the system connectivity and the tests that are having data driven also very important in terms of identifying the approach for the underneath framework. So generically the framework is developed uh, to avoid the huge dependency basically. So wherever the dependency is there, we try to minimize as much as possible so that the framework is generic and that framework can be used across the multiple functionality of the pieces of the software under the test. Okay. So design for maintainability, test data is stored in continuation of the test automation technique. We have a test suite, data driven framework. Then for maintainability purposes, test data is stored outside the test suite. Uh, the description of the test actions is separated from the technical implementation of these actions. I will show you a diagram which is uh, easy to understand. With the help of that, you can understand this description. The process of how to handle an automated test is implemented independent of its environment and system under test. This explains why any test suite needs several essential components. That essential components could be a test data and the framework and the test actions inbuilt within the test suite. The communication between the system under test and the test suite is implemented independent of the central process of the test suite. So you can see an example test and test automation environment, how it is going to look like. So it's just a depiction. So it doesn't mean that the same thing is used. In a nutshell, the system that is going to be tested is here. Is the system, and we have a repository of test cases. So all the test cases will have a database, spreadsheet, whatever it is, that will be picked up by the automation tool. It will pick up that and it will run on the system and it will generate the result. Basically, this is a flow where all the actions, checks, comparison, all will be done with the help of this test automation tool. And the data is stored outside. All the data, test cases, those things. So we know that the framework is part of this. This framework will pick up the test cases and it will apply the databases as per the inputs, and it will execute on the target here. And as a result of that, it will generate the report as a outcome of the test in a spreadsheet or Excel sheet or text document or the logging, whatever is required. Of course, also it will use the facility for the intricacies of the embedded systems, such as debuggers and all that. Everything can be automated with the help of the automation tool. Even the invoking of ID, debuggers, analyzers, logic analyzers, or scope also can be triggered with the help of this automation. All this we need, we know that. So if you automate it, it will be easier for us to maintain and design the testing aspects. So that's how testing is done. This is particularly useful where we have a complex embedded software system. So another variant of okay, so test cases are stored outside the test suite. Outside the test suite, yeah. they can store database in the spreadsheet here. And additional test case means adding only the test case to the storage of the test case. So if there is any additional test case we want to do, we don't have to change anything on this side. Only we have to add the repository or delete or modify whatever it is. So the test suite don't have to change. So the test suite will always be same. So another variant of this you can see in the next diagram where test actions and checks as part of the test automation tool will work like a machine, and the framework is outside. The framework is built little outside with more automation here. And the philosophy of test cases, database, spreadsheet on the left hand side in the repository. So the technical implementation of the test actions that are part of this are stored in the framework. You can see the blocks. These blocks can be a series of actions or the sequences. So that is written from the user of the test suite. So these are test suite basically. Again, the test suite will have a system trigger and specific test cases are picked up, and the framework will drive what needs to be done. So that is the difference between this and the previous one, where we have the framework separated from the automation tool. Of course, we can also call it as a independent automation tool. This bundle is very important here, where maximum automation is done with the help of framework and the action specific the tool. This tool could be LabVIEW, Test and or Simulink, or there are multiple tools available in the market. So basically, the technical implementation of certain test action can be rather complicated. So this implementation should be hidden from the normal user. You don't have to bother about where it is available. So only thing to know is which test actions are available. So those actions are a part of the automation. So automation will pick from the framework. So if the functionality of the system or the test stays the same, but the technical implementation is changed, suppose we have different implementation altogether on the embedded systems, so the framework will modify. So we don't have to modify the automation itself. So in that aspect, it will be useful. So for example, an additional interface is added, or signals have changed in their characteristics, etc. But user can still use the same script if nothing has happened. So in the previous example, we have seen that test data and actions are combined in one test script, whereas here we have separated out with the help of the framework. So that is the thing. Okay. Next one is the test suite. How it looks like, the intricacies of the test suite. Basically, it is also called in the book. It is specified by Embedded Software Testing by Bart Brockman and Edwin Notebook. I am referring most of the pieces there because that is more relevant what I see. You can refer this book online. And the suite has several components inbuilt. So let us see how it flows. So this is the basic what is that called framework, having different modules. You can see it here, and it has a flow. There is a start, there is a planner, there is a reader. So the planner will pick up a particular test scenario from the test data storage. That means we have a test data storage in terms of a database having signals, its definitions and all that, and the cases also, test cases also specifying the test scenario, and that scenario will be picked up by the planner module, and next one will be reader for that particular scenario. The particular test script will be read from the stored database or the contents. And there's a translator. Translator could be applying this into the understandable actions onto the target. So the test actions are derived from the translator. There's an intermediate layer. So the name is translator, but it could be anything when it comes to the actual embedded software testing automation. Different names could be used. So the actions could be initialization, synchronization, recovery, reporting, checking, and all that part of this framework having different modules. And as a result of test actions, we have the status report, and the actions will be applied on the target system under test. And the status report will tell that for each of the script and the scenario, what is the pass fail value, or the what are the passes and where it has failed. And also when we do the batch run, we can get the progress report in terms of pass fail count. It is called pass fail count, burn down progress. It's basically a chart of the entire test suite or the bundle of the test suite progress. So that is how we use test suite in terms of automation. So this is about the test suite. So where the framework and the automation is being combined in this diagram. It's also called as a blueprint of a test suite. Okay. In the next slide, we see different actions or the activities, how they are getting implemented. The simple blocks. Design stage of the test suite or the automation has this many blocks. So we need to define the objects, and we need to analyze test objects and analyzing the test approach. This is the first fundamental thing that we do. Then with the help of this defined objects and analyze the test objects and the approach, once we have finalized for each of the requirements of for the particular suite, then we are going to start the test suite with the design. So we'll start the design of the test suite. Then we'll have the construction of the test suite with the scripts or whatever it is. Once it is done, we reach the completion stage. So the major objective is to prepare an automated test environment capable of meeting the test automation objectives. In order to realize this, some activities are defined. First is the preparation of a plan of action. The purpose of being to show the activities, people involved, time estimation, etc. All is part of the first set of blocks. The definition of the test automation objectives, detailed analysis of test object and test approach are very much necessary for the design decisions. The decisions are also have to be taken care. What sort of an approach or any modifications are required from my planning. All this will be part of this. Also, parallel activities also can be executed as necessary. There could be similar functionalities where we don't need a separate approach, but slight modification in the inputs that also can be planned, so that it's very clear for the testers or the test development team to have what sort of an approach for different blocks of the underneath embedded system. All this will be part of the implementation. Okay, so that is about the test automation technique. The next one is we will study about risk-based testing. So what is risk-based testing and why it is needed? and some of the embedded systems they use this as an important testing. Okay, so basically, so what we do in risk-based testing is we will highlight or identify the importance of certain tests, which is very key in embedded software testing. Key tests and decisions and uh, any factors that are going to affect the outcome of the entire embedded software testing, so that the decision can be further taken in order to stop the test or continue the test or report it, or if it is a major uh, revoke of the embedded system so that it has to be completely fixed, then this risk based testing is very useful. So basically, developing a risk based test strategy is communication, basically communicating to the stakeholders what is most important about this system for the uh, product company or the organization, and what this means for testing of the system. That means instead of telling we do testing everything, so we will identify some of the key aspects of the testing, and that could highlight some of the business objectives also for the system under test. All this will be highlighted in this risk-based testing. For that, there will be a strategy for those aspects of the test, because there are a lot of factors that are involved in terms of resources. Resources could be people, money, time, and infrastructure. So that also we will highlight. Infra could be cost, and it could be human resource and schedule, etc. So if there is a major thing that needs to be taken care for these specific tests, all this will be strategized. So those are strategized under risk-based testing. The separate strategy that they will adopt for complex systems where certain functionalities have to be minimally working as a business objective. So basically, in a structured test approach, this is very important, and it contributes to a more manageable test process. Priorities must be set and decisions made about what is important and what is not is all being specified. Okay. So important means what? It's very subjective concept, of course. With a risk-based test strategy, evaluating the importance is about answering the question something like how high is the business risk if something is not okay in this test. That means if something doesn't work while doing the testing, so what is the impact of that? What is the importance of being that as not okay? So all answers for that will be part of the risk-based testing, and that should be communicated. So we need to define that. So basically, a risk is defined as the chance of failure occurred or occurring related to the damage expected when it does occur. So what is the damage that is going to cause for that particular failure? So if the system is of insufficient quality, this may imply high damage to the product. For instance, it could cause loss of market share. The company, it can be obliged to call back millions of sold products. You have seen there is a callback of Toyota cars for a small issue that they found near the brake. To replace that, they have to call back. It is called as call back millions of cars. So it is going to be a huge cost. So those will be identified while doing the uh, strategy of certain aspects. So in that aspects, the importance of those key elements will be identified. That's called risk-based testing. That will be under tests. Therefore, the situation forms a risk for the organization. Whatever the highlighted elements which are called as a risks. So testing of those aspects will cover such risks by providing insight into the extent to which the system meets the quality demands. So if certain areas or aspects of the system imply high risks for the product, then more thorough testing is obviously a solution. So thorough testing of that particular aspects are the important parts of the system is to be done. So those will be done from the quality standpoint. Of course, the other way also is true, where there is no risk is involved. We may have to have a small piece of a test, or if there is no test is required, we don't have to do a test when there is no risk at all. So how do we evaluate that no risk is involved, or risk is involved, or if it is important or not important? So this risk-based testing strategy will answer that. The attributes could be from the quality or the performance or the product outcome in terms of business objectives. So usability and all that will be part of this risk-based testing strategy. And the subsystems also could be come under risk-based strategy. We have a big system having subsystem 1, 2, etc. All this will be considered for failure attributes and the risks and the importance of that particular failures. And how they do is decomposition of the architecture, the high level information system. With the help of that, they will arrive at the strategy decisions. This is specifically done in with the help of quality attributes such as ISO 9126 and DO also they apply it. So it's very important to have decisions making factors for such important aspects of the system. Okay, so that is what is called as a risk-based testing. Risk assessment has to be done for the identified risks. So chance of failure into the damage it's going to have is what is called as a risk, and that will identify the particular test strategy for type of risks that are identified. So identify locations of where the faults tend to occur, such as complex components, components with many interfaces, signals, etc. So those need to be identified first, and identification of what are the chances of failure and what is the cost of the damage. So that will be arrived. With the help of that, risk will be assessed. So it's called risk assessment, very important part of the risk-based testing. And identification could be on some of these things like complex components, completely new components. If the people are not knowledgeable, or if it's a new subsystem that has come to market and that is getting used, that is a risk. And if the component is getting changed again and again in the board or in the embedded system, could be embedded software, it could be, and that is also a risk. Components for which certain tools or techniques were employed for the first time, and components which were transferred from one developer to another developer during the development, there is a chance that the new developer would have injected some failures. Components that were constructed under extreme time pressure. It's a very important term because What will happen is in embedded software development, there is a chance that the last minute work will be more, and due to delays in inputs for the developer or the tester, uh, due to high pressure, and time to market, the chances of injecting the failures are more. And those components need to be identified as risk components or risk elements. And here component means it is not the hardware component, it is any piece of the embedded software system. So components which had to be optimized more frequently than usual. That means more optimization is required on those components that also can come under a risk. Components in which many defects were found earlier. uh, Example, previous release or during earlier reviews, we saw that certain components are having high defects. Still, that has a high risk. Components with many interfaces, many signals are being used in that components. That is also a risk element. So the chance of failure is also greater for the inexperienced developers, insufficient involvement of user representatives, insufficient quality assurance during development, insufficient quality of low-level tests, new development tools and new development environment also is a risk. Large development teams where segregation is very difficult and interaction of different teams also is a risk. Development teams with a suboptimal communication, example, owing to geographical spread. That means we have seen embedded industries spread across uh, geographically different locations, such as in aerospace industry, we develop the entire system. Example in Boeing, it is done in Seattle, USA, whereas development is done in a different location in USA, and testing is done in India, and fabrication and assembly is done in China. So the development team or the testing team is completely disintegrated, and interaction have to be done efficiently. So as long as that is there, the chances of failures are more, due to which there could be slack in some of the communication or convincing the facts. So there will be some hidden issues or errors that system can have. Components developed under political pressure with unresolved conflicts in the organization or shufflement in the team also could be a fact of risk basically. Okay, so that is about risk-based testing. We come to the slide where how we can treat the risks. That is a term called risk mitigation. I think it is all management aspects. We will not study in detail, but at least for an understanding sake, we'll try to work through risk mitigation and risk contingency. It means we anticipate the risk, and we will work out what best we can do in the contingency, and risk mitigation is if the risk occurs, what would be our approach. So it is part of the risk management. So what are the options that are available? So categorization is something like this. So the required information for risk assessment is usually obtained from different sources, and with the help of those sources, we will arrive at different risk management options. So we have a broader categorization as minimize loss or pay for loss. So here again the complexity which matters. So based on that, the risk options are derived. Okay. So minimize loss is what is one category of treatment of the risk. where loss prevention and loss reduction and any threats we have will be done with the help of certain mitigation plan. So that will work out for the loss prevention. And in loss reduction, system engineering, risk assessment program, design reviews, test, analyze and fix, well structured test and evaluation. So all this will be part of the loss reduction. So we are going to have a loss for certain failures. How we can reduce it? So these are all the aspects which can be treated for reducing the risk. And as we progress towards embedded software testing, we should try to reduce the risks. That means loss prevention and try to avoid threats that are there for the particular system. So this is only one path where we are trying to minimize the loss. And already the loss has occurred and the failures are there, risk is realized, then we have to pay for the loss. So how are we going to de-risk it or treat it? So risk retention, cost and schedule reserves. That means we have a reserved cost for that. We are going to retain that risk and we are going to pay for it, or we are going to transfer that risk so that somebody else can continue on. So this is basically a management thing, and if that is coming under warranty and all that, as part of that, it is taken care. So risks are very high element, important thing in the embedded software testing as a management aspect. So that need to be mitigated and contingent. Okay. So that is about risk-based testing and the risk-based testing aspects and test strategy. And we have a couple of important things that is used in embedded software testing method. That is called formal and informal testing. So what is the formal and what is informal? And the other aspect is dry run and formal run. Okay. So these two are being used again and again in the embedded software industry. We'll try to understand what is formal, what is informal. A formal test design technique has strict rules on how the test cases must be derived, documented, or process-oriented rules that will be documented, reported, and frozen. So strictly we are going to follow that in formal test design technique and execution. The advantage is that it minimizes the risk that the tester will forget something important and all that, because everything is based on a laid out process. So different testers using the same formal test design technique should produce the same logical test. That means we have a chain or the cycle that is well defined. So the user will follow that and he don't have to bother anything outside that. So testers will use the same formal method or the design technique again and again for doing the test and producing the results. The disadvantage is that the test cases can only be as good as the specification they are based on. A poor system specification will lead to a poor test because we have already committed to doing the test and we don't have any second chance for revisiting the specification or the test design. So the failures, if it is going to happen, it is going to happen. An informal test is the another one is a design technique that gives general rules and leaves more freedom to the testers. That means informal test, the tester has second chance of revisiting this test approach or technique and he can slightly modify, or there is a scope for improvement. There are hooks where he can adopt some changes or propose some changes. There are what is that called? Templates where he can provide proposals to modify it and still there is a chance that we can improve the product before the product is out for delivery. So this places more emphasis on the tester's creativity and gut feeling about the possible weakness of the system. That means the tester will have a full confidence of the embedded software system. It usually requires specific domain expertise. As I said, very much it is important to have the system knowledge or the domain. Here, domain means it is not just about the product and the product line. Where it is being used. The product could be used in certain avionics subsystems or systems. It could be used in engine types. Could be used in weather forecast. It could be used in braking, because braking has many some small subsystems. So that our test what we are doing could be part of that underneath that, and we have telecom. We have gadgets such as home entertainment or set-top box, whatever it could be. So all this will be requiring to have a thorough knowledge of the domain of that particular embedded series where the product is being developed, tested, and deployed. So informal test design techniques are less dependent on the quality of the test basis, but have the disadvantage that they provide little insight into the degree of coverage in relation to the test basis. That means everything will be informal. The coverage we cannot take the credit. Tests and its outcome. Simply because whatever the tester has done in the informal testing is all intermediate ones. It is not the frozen ones or the final ones. So that is where it has a disadvantage, but it is advised to have an informal test before we start the formal test. The flow should be something like we begin with informal test, identify all the weaknesses, get a good confidence on the entire system, understand the domain, apply the techniques, improve the techniques, optimize it, and anything that we want to do before we actually do the formal test. So they use it in the embedded system industry, formal and informal. These two terms. It's equivalent of that are being used in specific industry that is called dry run and for formal run. The informal one is called as a dry run, that is the first cut run of the primary test execution. So basically it gives a confidence, and any revisit is required, fine tuning is required, all will be done with the help of this dry run. It's something like an informal or pre-formal run, and there are different names that are used, but generally in the ML industry they use it as dry run and formal run. We know it is same as whatever we have studied in the previous bullet. Formal run is the execution of tests with evidences captured as it is going to be reported with the complete documentation. So once we are done with this formal run, that is what is going to matter in terms of reporting, pass, fail, revisit, whatever it is required. So that is about the testing terminology used in the embedded industry called formal and informal, and dry run and formal run. So with that we come to the end of unit 1. So probably we'll touch base what are the chapters we visited so far in the next session. So before concluding the class, I will go through some of the glossary that we have for today. Test action, part of a test case which defines the actions that must be performed on a test object. Test automation, we have seen use of software to control the execution of tests, the comparison of actual tests, actual results, the expected results, the setting up of test preconditions and other test control and test reporting functions. Test basis. All system documentation used as the basis for designing test cases. Test bed, software, hardware, is both that offers stimuli to a test object and records the output from that. Test case, we know that it is set of inputs, preconditions, and expected results designed for a particular objective or a requirement, such as to exercise a particular program path or to verify compliance with a specific requirement. We know that requirement level, we have a high level test or a black box testing. We will have a test cases accordingly, and for white box testing, we will do the coverage and all that while doing the execution on the implementation of the code. Test infrastructure, the environment in which the test is performed, consisting of hardware, system software, test tools, procedures, etc. So with the help of infrastructure, we develop or build the environment. It also has a automation aspects in all that. Test level, we have seen in our earlier sessions, a group of test activities that are organized and managed together. A division can be made into high level or low level tests. Then we have a test depth level, indicates to what extent the dependencies between successive decision points are tested. At the test depth level n, all dependencies of actions before the decision point and after n-1 decision point are verified by putting all possible combinations of n actions in that test path. So that is about the glossary that we have discussed today. So with this, we come to the end of this today's session and the units that we have completed, Unit 1 and Unit 2. We will do a small recap of whatever the units and the sessions we have completed, and we will take up the next unit, that is static analysis, inspection and reviews in the next session.